So let's get right into it. Have you ever looked at a messy spreadsheet and thought, how on earth does this become a smart AI that can make predictions? Well, today we're going to tackle exactly that. We're diving into the most important and honestly, the most time consuming part of the whole process data preprocessing.
And get this, here's a number that always blows my mind. Sources show that data scientists can spend a whopping 80% of their time just cleaning and preparing data. Yep, that's right. Not building the cool models, but just getting the data into shape. So, why is that? Well, it all comes down to one simple, unavoidable rule. You've heard this a million times, I'm sure, but in machine learning, it is the absolute gospel truth. You could have the most sophisticated, powerful algorithm in the world, but if the data you feed it is a total mess, your results are going to be, well, garbage. Simple as that.
To really get a handle on this, let's put on our lab coats and think like data doctors. Because in the real world, data never shows up in perfect health. It's always got something wrong with it, and our very first job is to give it a full checkup, to diagnose the problem before we even think about a cure. And when we put our data under the microscope, we usually find three very common ailments. First, there's what I like to call data amnesia. Missing values all over the place. Then you've got a high fever. These are those crazy, extreme outliers that can totally warp our results. And finally, uneven growth, where our data features are on completely different scales, which just throws the whole system off balance. So, to make this all feel real, we need a patient. And for that, we're going to use the famous iris dataset. It's a classic, a go-to for machine learning. But to make it realistic, we've deliberately made our patient sick. We've gone in and injected it with all those problems we just talked about.
And here they are, the initial lab results. This table gives us our first major clues. Just look at that count row. See how the numbers are all different? That's a dead giveaway that we have missing values. That's our data amnesia. Now, check out the max value for sepal length, 10.9 centimeters. That looks really high compared to the average. That's a textbook symptom of a high fever, a nasty outlier. Okay, diagnosis is done. Our patient is definitely not feeling well, so it's time to roll up our sleeves and get to the treatment plan. We're going to grab our data doctor's toolkit and tackle each one of these problems one by one.
First up, let's treat that data amnesia. These are just gaps in our data set, often shown as NaN, not a number. And trust me, if you leave these in, they can totally confuse your model or, in a lot of cases, just break it completely. We have to fill in those memory gaps. So, our first tool from the kit is called a simple imputer. The game plan here is actually pretty straightforward, but super effective. For every blank spot in a column, we're just going to fill it with the average, or the mean, of all the other numbers in that column. It's kind of like helping the patient remember by prompting them with the most common answer. All right, next up, we have to deal with that high fever. Outliers are just extreme data points that are way, way out there compared to everything else. Sometimes they're real, sometimes they're just errors, but either way, they act like a magnet, pulling our model's understanding way off course. Just think about it like this. Imagine you've got 10 people in a room, and you want to find the average income, but one of those people is a billionaire. Suddenly, that average income is ridiculously high and doesn't actually represent anyone in the room. Well, that's the exact same headache our models face. One crazy data point can wreck the whole thing. So how do we bring that fever down? We use a neat statistical trick based on something called the interquartile range, or IQR. Now, instead of just deleting the outlier, because we don't want to lose information, we cap it. We figure out a reasonable upper limit, and any value that flies past that ceiling just gets brought back down to it. It tames the wild value without erasing it.
Okay, 2 problems down, 1 to go. Let's talk about our last ailment. What happens when your data features are measured in totally different ways? Like, what if you're trying to compare a person's age with their yearly salary?
Right, so imagine you're looking at age, which goes from maybe 0 to 100, and salary, which could be up to 1 million.
Any model that works with distance is going to look at those huge numbers for salary and think, whoa, salary must be thousands of times more important than age. That's our uneven growth problem. The cure is to get everything onto the same balanced scale. And the perfect tool for that job is the standard scaler. This is a fantastic technique that reworks every feature so that it has an average of 0 and a standard deviation of 1. What does that actually mean? It just means we're creating a totally level playing field, making sure no single feature bullies the others just because its numbers are bigger. So, we've diagnosed the issues, we've administered all the treatments. Now, for the moment of truth, it's time to check on our patient and see what a full recovery really looks like. And you see, this isn't just a bunch of random fixes. It's a solid, repeatable workflow. Step 1, fill the gaps. Step 2, tame the extremes. Step 3, level the playing field. This 3-step recipe is really the heart and soul of most data pre-processing work. Now hold on. Before we see the final results, there is one golden rule that you absolutely cannot forget. You calculate all your fixes, the mean, the outlier caps, the scaling numbers, using only your training data. Then you take those exact same rules and apply them to your test data. Why? Because doing it any other way is like giving a student the answers to the test before they take it. It's cheating, and we call it data leakage. All right, that was a lot of work, so you gotta be asking, was it all worth it? Did all this data medicine actually make our model any smarter? Well, let's take a look at the payoff. And there you have it, the proof is right there. Before we did anything, our model's accuracy on the messy data was pretty mediocre, just 75%. But after our 3-step treatment, the accuracy skyrockets to 95%. I mean, that is a night and day difference, and it's all thanks to giving our model clean, healthy data to learn from. And really, that's the whole point, isn't it? Pre-processing isn't just about tidying up. It's about bringing clarity. By getting rid of all that noise, the missing values, the crazy outliers, the skewed scales, we let the model finally focus on the real patterns hidden in the data. We're just removing all the distractions so it can finally do its job properly. So our data is healthy, our model is smarter than ever, and our accuracy is through the roof. Which brings us to the most exciting question of all. Now that our foundation is solid, what incredible secrets is our data finally ready to share with us?